Welcome to Module 2, Session 1 of Engineering Statistics and Linear Algebra course. The course learning objectives of Module 2 are understand and analyze multiple random variables and their extension to random processes. The contents of Module 2 are two variable or bivariate CDF and PDF, bivariate expectations, bivariate transformation, bivariate Gaussian random variables, sum of two independent random variables, sums of IID random variables. IID stands for independent and identically distributed random variables, central limit theorem, law of large numbers, conditional joint probabilities, and lastly, we'll look at application exercises. Here, we'll look at 4 special random variables. Now we'll look at the contents of session 1. Firstly, we'll understand what is bivariate random variables. Afterwards, we'll look at bivariate CDF and bivariate PDF. Once we study the bivariate CDF and PDF, we'll look at some problem examples. And lastly, we'll look at the assignment questions. Now, we'll understand what is bivariate random variables. By this time, you are already introduced to some of the terms like sample space, random experiment, and random variables in module 1. Right? Now, here we'll study what is bivariate random variable. Now, let us consider the sample space S of the random experiment, and let X and Y be the random variables. Then this pair of random variables X and Y is called as bivariate random variable or two-dimensional random vector if X and Y associates a real number with every element of the sample space. Yes. Then these two random variables, X and Y, the pair of X and Y is called as what? Bivariate random variables. In simple terms, if both these two random variables, X and Y, are considered at once, we say that these two random variables are bivariate random variables, right? The range space of this bivariate random space is denoted as Rxy, which is given as Xy for A belongs to the sample space, and for Xa is equal to X and Ya is equal to Y here, right? Now, what could be the examples for bivariate random variable? The first example could be like, consider the input to the system at time t1, which is a random variable X, and output from the system t2, which is a random variable X. Then these two random variables X and Y are called as bivariate random variable. The one more example could be like working simultaneously with the signal random variable and noise random variable. Consider the signal random variable as X and noise random variable as Y. Then these two random variables considered at once, the signal and noise, we call it as what? Bivariate random variable. Right? Now, since we know what is bivariate random variable, now we'll look at bivariate CDF. CDF stands for what? Cumulative distribution function. Now we already studied what is cumulative distribution function for a single random variable. Right? Now, how it is defined as? The CDF is always written in capital F. Fx of X is equal to the probability of X less than or equal to X. The same concept is applied for two variable or bivariate random variable. Now, how do you write for this one bivariate CDF? Fxy of X comma of Y, this is equal to the probability X less than or equal to X and or intersection Y less than or equal to Y. It means that when I say intersection or and, it means that both these two conditions has to be satisfied there, right? This event for X less than X and Y less than Y, this event is shown in the diagram here. Similarly, now for a bivariate CDF, which is evaluated once, now we know the CDF fx of x comma y, which is evaluated at x comma y. Now, once again at x plus dx, y plus dy. Now, how do you find the bivariate CDF, which is evaluated at x plus dx, y plus dy, right? Now, how do you do this one? It is given as dp, which is fx of x plus dx, comma y plus dy minus, and now this is already evaluated at x and y, fx of x comma y. Now this is equal to what? Dou by dou x, fx of fxy, x comma y dx plus dou by dy, fxy, x comma y dy. Now we'll look at the properties of bivariate CDF. The first property is the bivariate CDF is non-decreasing in both the x and y directions. It is non-decreasing in both the x and y directions. And the cumulative distribution, the bivariate cumulative distribution, fxy, x comma y, lies between the 0 and 1. Right? The event, the third property is the event x less than equal to minus infinity. Right? It means that the x taking the values less than equal to minus infinity. The x cannot take any values which is less than minus infinity, so that it is impossible event, and that is represented as a null or null set. Therefore, how do you write the bivariate CDF? fxy, x comma y is equal to the probability. And what is x less than equal to minus 0? It is an impossible event, so that it is a null intersection, or and y less than equal to y, so that now since it is an intersection, this is equal to 0, so that this is evaluated as probability of null. Probability of null is equal to 0, right? Similarly, now how do you write for this one? fxy, x comma minus infinity. Again here minus infinity means what? The y less than equal to minus infinity. It means that the y taking the values less than minus infinity. Again, that is an impossible event, so that this is again, this is equal to 0. Similarly, when both x and y taking the values less than minus infinity, again that is an impossible event, so that fxy minus infinity comma minus infinity, this is also equal to 0. Right? Now, next property, the event x less than equal to infinity. When I say event here, x less than equal to infinity, which is nothing but a certain event in the sample space, yes, and this is valid for any y on the xy plane. Therefore, how do you write for this one? For x less than or equal to infinity, you can write it as fxy infinity comma y. Now, since x is less than or equal to infinity, this is nothing but you can write it as the sample space ANDed with y less than or equal to y. Now, since it is ANDed with s or intersection with this one, now how do you write now this one? P y less than or equal to y. This is equal to fi of y, right? It means it has reduced to single random variable y, the cumulative distribution function for single random variable y here. Now, similarly, if y is less than or equal to infinity, now how this bivariate random variable reduced to fxy x comma of infinity for y less than or equal to infinity. Now this will be reduced to what? Fx of x, single, this the CDF for single random variable x. Now this fx of x and fy of y are called as what? Marginal CDFs. Next property, if both x and y are arbitrarily large, it follows from the above equations as, now here both x and y are less than or equal to infinity. Now this cumulative distribution function is equal to 1 when both x and y are less than or equal to infinity. Next property, the two random variables x and y will be called independent if fxy x comma y is equal to fx of x multiplied by fy of y. Then these two random variables x and y are called as what? Independent random variables. Since now we studied bivariate CDF, now we'll go to the bivariate PDF. PDF is probability density function. Now, similar to the single random variable, what we studied for PDF and CDF, the same concept is applied here also for bivariate PDF and CDF. The bivariate probability density function of two continuous random variables x and y is defined as the following derivative of the bivariate CDF. So that, as I said, for this one, the PDF is defined as small case f of xy, x comma y. This is equal to dou square divided dou x dou y, fxy, x comma y. This is similar to what we studied for single random variable. For discrete or mixed bivariate CDF, two-dimensional unit impulse functions are used to represent derivatives of discontinuities in the CDS. If it is discrete random, if both x and y are discrete random variables, or mixed. When I say mixed, it means that one random variable could be discrete, the other random variable could be continuous. At that time also, we use two-dimensional unit impulse functions are used to represent what? Derivatives of discontinuous in the CDF. The marginal PDF for x and y is given as fx of x is equal to integration minus infinity to infinity fxy x comma y dy. Similarly, what is the marginal PDF for random variable y? Fy of y is equal to integration minus infinity to infinity fxy x comma y dx. Now we'll look at the properties of bivariate PDF. The bivariate PDF is a derivative of non-negative function, that is bivariate CDF. When I say non-negative function, the bivariate CDF is non-negative, right? We know that the bivariate CDF is non-negative, right? It's non-decreasing in both x and y direction. Its value is always as positive. Therefore, the bivariate PDF is always as non-negative. Now, how do you represent this one? fxy x comma y, which is always greater than or equal to 0, which is always non-negative in the range minus infinity to infinity. The bivariate CDF could be obtained from the bivariate PDF using inverse relation. Now here, in the definition of bivariate PDF, I have defined as what? The small f is nothing but the derivative of the bivariate CDF. So that in order to get bivariate CDF from this one, it is nothing but the integration minus infinity to y, integration minus infinity to x, and the bivariate PDF du dy here, right? This is how you can get the bivariate CDF knowing the bivariate PDF. The next property, the total volume under the surface of the bivariate PDF is equal to 1, right? The total volume under the surface of the bivariate PDF is equal to 1. Now, how do you represent this one? When I say total volume, fx of infinity comma of infinity, this is equal to minus infinity to infinity, integration minus infinity to infinity, fxy x comma y dx dy. And this integration is equal to what? 1 here. Right? Next property, if the random variables x and y are independent, if both the random variables and x and y are independent, now how this is represented? fxy x comma y is equal to what? Probability x less than x, probability of y less than equal to y, right? Here, both these two random variables are independent. That's the reason we've written as probability of x less than equal to x, probability of y less than equal to y. Now, what is this probability of x less than of x? from the definition of single CDF, this is written as fx of x. And for this probability of y less than or equal to y, this you can write it as fy of y. Right? These are the properties of bivariate PDF. Now we'll look at some of the problem examples related to bivariate CDF and bivariate PDF. First example, find the bivariate CDF fxy x comma y in different regions and marginal density fx of x and fy of y for the given bivariate PDF. Now, what is the expression which is given here for bivariate PDF? fxy x comma y is equal to 1 for xy lying between the range 0 to 1, and for other cases the bivariate PDF is equal to 0. And also you need to find whether these random variables x and y are independent. Right? The first, here you need to find fx x comma y in different regions. Right? Now, just by looking at this one, we know that the given PDF is nothing but a square. Right? The square is represented here. Right? It means that the values of x and y lies in this square shaded region here. Right? Now, you need to find the value of bivariate CDF fx x comma y in different regions. For different values of x and y, you need to find what is fx of x comma y, and also you need to find fx of x and fy of y. Once you find fx of x and fy of y, again you need to find whether these two random variables are independent or not. Right? Now, the first region. Right? Now, whenever xy is to the left of y-axis or below the x-axis. In the sense, now to the left of y-axis, this shaded region, right? Or below the y-axis, this region, right? Now, if you see in the given example, the value of x and y lies between what? X and y greater than 0, x and y less than 1. So that anything below 0, right? It means to the left of y-axis, this region, right? And below the y-axis, this region, the bivariate CDF is what? It is equal to 0 because it is only defined as the square region here, right? So that for anything x less than 0, for anything y less than 0, the bivariate CDF is equal to what? It is equal to 0 here, right? This is the first region. For this region, for x0, y0 less than 0, the bivariate CDF is equal to 0 here. Next, for region 2. Here, for region 2, I'm considering whenever x, y is to the right of x is equal to 1 and above y is equal to 1. In the sense, when x is greater than 1, right, and y is greater than 1. In the sense, what is this region now? It is this region. X greater than 1, y greater than 1. This region. Right? For x greater than 1 and y greater than 1. Now for this one, now here the bivariate CDF will always be 1. Why it will always be 1? Because the unit square is always included in the integral of the CDF equation here. So that this for values of x greater than 1 and y greater than 1, for this region, this region, what we have, this region, right? The bivariate CDF is always equal to 1. Next, for region 3, here, whenever xy is in the strip for y greater than 1 and the x lies between the values 0 to 1. That is, whenever xy is in the strip which lies to the left of x equal to 1 and above y equal to 1 here, or y greater than 1, and for this x less than equal to x less than equal to y. Now for this region now, for y greater than 1 and x lying between what? 0 to 1 here. So that how do you for this one now? This region above y greater than 1, this region. Now for this region, how do you find it now? It is 0 to 1. For this range of y, it is 0 to 1. And here the x value is between what? 0 to 1. So that you write it as 0 to x because it lies in this shaded region. So that it is 0 to x f xy x comma y du dy dx dy du dy. Now how do you write this one? F xy x comma y, this is equal to integration 0 to 1 0 to x. Why it is 0 to 1? Because y is greater than 1, and why it is 0 to x? Because the x is lies between 0 to 1. And what is this value now? It is equal to 1 du dy, right? Now integrate this one 0 to x 1. This you get it as x here. Integration 0 to 1 dy, so that you get it as 1. And again you evaluate the integration 0 to 1 x dy. This is equal to x. And this now the bivariate CDF value is equal to x for y greater than 1 and the x lying between the value 0 to 1 here. Next region we'll consider. Here I'm considering the value of x greater than 1 and the value of y lying between 0 to 1. Since the y value is lying between 0 to 1, integration is what now? 0 to y here. And x value is greater than 1. So that it is equal to integration is 0 to 1 here. Fx of x comma y dx dv. Fxy x comma y is equal to integration 0 to y 0 to 1. Evaluate this one, right? Now since double integration, evaluate this one. Here you get it as y, and again it is 0 to 1 and 0 to y we have it. So that evaluate the integration, you get it as y here. So that for the values of x greater than 1 and the value of y between the range 0 to 1, this is equal to 1 here. And everyone understood this one for region 4. Next, for region, for x lying between 0 to 1 and the y lying between 0 to 1. Now here for integration is how do you write the integration for x lying between 0 to 1? You write it as 0 to x. For y lying between 0 to 1, you write it as integration 0 to y. Now evaluate this one, you get it as x, y here, right? So that now all the 5 regions, the region 1, 2, 3, 4, and 5, all the regions what we discussed till now, that is summarized in this diagram here. And what are the values we got now here? It is the bivariate for fxy x comma y is equal to 0 for xy less than 0 for this region, and this is equal to 1 for xy greater than 1 for this region, and this is equal to x for y greater than 1 for this region. You can see here it is x, and for x greater than 1, this is equal to y, and between the range x and y, between the range 0 to 1, this is equal to x, y here, right? Next, what we need to find now? Now we need to say whether these two random variables are independent. Now we already calculated fxy is x comma y, which is equal to fx of x, fy of y. Now this is equal to what? Xy, and this is also equal to x, y here, right? If I integrate this one, fx of x, you get it as x, and fy of y, you get it as y here, right? So therefore, you can say that the given bivariate random variables x and y are independent here. Now we'll go to the second example. The joint PDF fxy x comma y is equal to c, a constant, when x lies between 0 to 3 and y lies between 0 to 3 and is 0 otherwise. First, you need to determine what is the value of the constant c. Secondly, you need to find what are the PDFs for x and y. Thirdly, what is fx x comma y when x and y lying between 0 to 3. What are fx of x comma of infinity and fxy infinity comma y. And lastly, you need to say whether x and y are independent random variables. Now, how do you proceed this one? From the given problem statement, we have written the PDF as fx of x comma y is equal to c between this range, and it is equal to 0 for other cases. Now, from the property of bivariate PDF, we know that the total volume under the surface of the bivariate PDF is equal to 1. So that how do you write this integration now? 0 to infinity fxy x comma y dx dy is equal to 1. Now here the range is given for x as 0 to 3 and y also it is 0 to 3. So that how do you write this one? 0 to 3, 0 to 3, c dx dy, this is equal to 1. Now evaluate this double integration. Evaluate this one, what you get? This is 1 c, and evaluate the integration, limits is 3 and 0. Cx 3 is 0, dy is equal to 1, so that you get it as x taking the value of 3. 3c dy integration 0 to 3, this is equal to 1. Now evaluate this integration, you get it as 3cy with the limits 3 to 0, this is equal to 1. So that 3 into 3 will be 9. 9c is equal to 1. So that the constant c value is equal to 1 by 9. Right? The first, what we need to calculate is the value of the constant c. So that what we found here, the c value is equal to 1 by 9. Next, we need to find the PDF for x and y. Now, how do you find the PDF for random variable x now? What is the formula? Fx of x is equal to integration minus infinity to infinity fxy x comma y dy. Now, what is this fx of x comma y? It is nothing but c, and the range is 0 to 3 here. Now, so that evaluate this integration, you get it as cy with the limits 3 to 0. You get it as 3c. And now substitute for the constant c now. What is the value of constant we found? It is 1 by 9. Therefore, 3 divided by 9 will be what now? 1 by 3 between this range. Say that what is the PDF for the random variable x now? Fx of x is equal to 1 by 3. Now, similarly, the PDF for random variable y, right? Formula is fy of y is equal to integration minus infinity to infinity fxy x comma y dx. Now, this is equal to the limits 0 to 3 c dx. Evaluate the integration, substitute for c, so that 3 by 9 will be 1 by 3 between the range 0 to 3 for y. So that what is the PDF for random variable y now? You get it as 1 by 3. The PDF for random variable x and the PDF for random variable y, both are 1 by 3. Now, once we do that one, next what you find now? You need to find the value for fxy when between the range 0 to 3. Now, how do you find between 0 to 3 now? Now, minus infinity to y, minus infinity to x. Now, in the previous example, how did we find for x lying between 0 to 1 and y lying between 0 to 1? The integration will be from 0 to y for y lying between 0 to 3 here. And similarly for the integration 0 to x for x lying between 0 to 3. And what is this bivariate CDF? It is given as c dx dy, right? Evaluate the double integration for this one, evaluate this one, substitute for c, you get it as 1 by 9 x y here, right? Now, the fourth what we need to find is for fx for x comma of infinity. Here, fxy, x comma of infinity is nothing but what now? We know that it is nothing but fx of x. We already seen the properties of this one. If y, right, is this infinity here, this is fx of x. Now, fx of x, how do you find it now? It is nothing but the maximum value of y is 3. So that what can write it as 1 by 9, 3x, for x by 3. Therefore, fx of x is equal to fx of x comma of infinity. This is equal to x by 3 here, right? Now, similarly for fx of infinity comma of y. Now, x is infinity. Now, how do you find it here? Here, it is lying between what? 0 to 3. So that the maximum value what we can have for x is, what we can have for this one is 3 here. So that what we can have 1 by 9, 3y, right? If we can integrate for this one, you get it as 1 by 9, 3y, and 3 by 9 will be y by 3. So that fy of y is equal to what now? Fx of infinity comma y is equal to y by 3. Everyone understood this one? Y, the maximum value of y is 3 because the range is 0 to 3 here. Similarly for this one, the maximum value of this one is 3, right? Next, lastly, we need to find whether these two random variables x and y are independent. For if these two random variables are independent, what is the formula we have? fxy, x comma y is equal to fx of x, fy of y. Now this could be written as xy divided by 9. Now this could be written as xy comma of 9. Here we know that this is xy by 9. And what is the fx of x is x by 3. And what is fy of y? You get it as y by 3. So that it is again equal to x multiplied by y divided by 9. So that we know that fxy of x comma y is equal to what? Fx of x multiplied by fy of y. So that we can say that these two random variables x and y are independent random variables. These are the two assignment questions. Please solve this assignment questions. Thank you.